All right, welcome everybody to our fall 2021 semester of New England Dynamics and Number Theory seminar. I'm very happy to see each other, to see you and to be able to see each other. And the first talk is given by Jayadev Athreya from the University of Washington and also Pacific Institute of Mathematical Studies. Well, I'm supposed to remember the title. It was about
point processes. Yeah, I don't even really remember the title. I'm just going to give a bunch of examples.
Point processes and geometric structures or something like this. Anyway, Jayadev, back to you.
Thank you. It's so nice to see so many familiar faces. I like Dima said, it'd be really wonderful if we can all see each other in person sometime soon. But in the meantime, Zoom will do. And yes, please do feel free to interrupt and ask questions at any point. I'm going to try and give kind of a big picture overview of some things I've been thinking about recently, all of which kind of center around the idea of variance. And this is very much inspired by a point of view that I think I originally learned from Jens, which is to think about point processes, thinking about certain families of points in Rn as analogs, or actually explicitly as probability measures on spaces of sets of points in Rn that arise in a variety of situations. And I think, maybe this point of view in some sense at least goes back to Veech, who, if you hear nothing else from this talk, there's it's not an easy paper to read, but there's an amazing paper by Veech called Zegal Measures, which you can actually describe. Probably for me, a lot of my mathematical career is going back to that paper, trying to read some section of it, and then trying to think about how it might work in a situation I'm thinking about. And that's not to say I understand this paper fully at all. In fact, I don't, but that's what's kept my research career going for some time. So if nothing else, you should look at this paper by Veech called Zegal Measures. It's very, very interesting. Okay, so let me be a little bit less vague and say what I want to think about today. I want to say, very broadly speaking, I have some space X, which is some space of geometric structures on a fixed manifold, on a fixed topological manifold. So it's some kind of moduli space. And then I'm going to have a map from X. I'm going to say sigma from X to the space M on some Rn, where M of Rn is the space of, for right now, let me say, since all the examples I'm going to talk about are going to be this, of atomic locally finite measures on Rn. So this is not terribly standard notation, but I'm just going to use it for this talk. So M of Rn is the space of atomic locally finite, let's say Borel measures on Rn. So, you can think of it as a collection of points with some weights, if you want. And what we're going to think about a lot in this, so this is now all kind of very abstract nonsense, but I'm going to get to some very concrete examples in a minute. And, maybe I also have some mu, which is maybe some probability measure on X. Okay. Then what I want to do is I want to think about sort of sigma star mu as a point process. Right? So what it is saying you have a way of picking one of these random geometric structures. Associated to this random geometric structure, I have some collection of points in some Euclidean space. And it doesn't have to be Euclidean space, but the examples I'm going to talk about today are Euclidean space. And then I want to think about pushing this measure forward, the measure on the idea of a random geometric structure to give me an idea of some sort of random collection of points with weights in Rn. Right? And this is just a point of view that unifies several things that I've thought about over the last several years. And so now I want to give some examples and tell you why it's kind of useful, and then what kind of questions come up when you're motivated by this point of view. So, okay, so this is maybe the abstract nonsense part of the talk. Abstract nonsense. Okay, so concrete example 1 is one that I think this audience will like a lot, is let's let X be SLNR mod SLNZ. This is the space of flat metrics on an n-dimensional torus, if you like, space of, or if you can think of it as the space of unimodular lattices in Rn, or space of flat n-dimensional tori, together with, there's a little bit of extra data here, right? I'm not quotienting it out by SON here. So this is together with a kind of a choice of direction. So plus maybe some idea of direction. So this is the space I want to talk about. And then what's my map sigma? So sigma, the map from X to the space of, let's say, there's a couple of different ones that we could look at. We could look at sigma of a lattice, let's say, I'll say G. I'm going to write GZN here just because I'm going to say, instead of writing GSLNZ, I'm going to just think of it as actually the lattice GZN. So I have this point in the coset space, but I think of it as the lattice sigma of GZN. Well, you could do this one. You could say summation over all non-zero vectors in Zn delta measure at GV. Or you could also do this another one. So this is maybe sigma. I could call this sigma all. And then we could do sigma prim of GZN would be summation 0 not equal to V in Zn. Well, I could just say V in Zn prim. 0 is not a primitive vector. V in Zn prim delta GV. Right, so this is the usual assignment that says, hey, to a lattice, associate, well, the lattice, right? And this is clearly well-defined on the space X, SLNR mod SLNZ, because if I multiply G on the right by something in SLNZ, I get the same measure. So what I'm saying is, think about this as a collection of measures on Rn. And then I can take mu to be the Haar probability measure on on Xn. So let's call this Xn here. On Xn equals SLNR mod SLNZ. And now I can ask questions like, what are some kinds of questions we can ask? So there's, of course, these extremely classical questions one can ask. You can say,
Jayadev,
sure.
Can I just ask, so the whole, I guess one of the reasons why this is interesting is that this sigma happens to be, so X happens to be G space and sigma is G equivariant.
That's right.
This is part of your abstract nonsense? Or
it is not part of my abstract nonsense because there's going to be an example where we don't have G equivariance when we talk about curves on hyperbolic surfaces. So, but this is actually a really good observation. So here, and we have G equivariance of the assignment. G equivariance of the assignment, and that will be a common feature to 2 of the 3 things we're going to talk about, but not the 3rd one. So G equivariance, it's where G is here, SLNR. This is actually a really good point, right? So maybe I'll just emphasize this. So you have this, Xn, we have this map from Xn to M of Rn. SLNR, either of these assignments, either sigma all or sigma prim, SLNR acts on this whole picture, and this acts on Xn. SLNR acts on the space of probability measures in Rn, or the space of, locally finite measures in Rn, and this map is equivariant, right, under this G action. But that's not going to be the case in all of the examples I look at. It'll be the case, like I said, of 2 of the 3 examples that we look at. All right. So what are some questions you can ask about this kind of question? And let's go back to some very classical things. It's funny, I was actually also talking to some people yesterday, and they said that one of the nice things is as you kind of become, as you kind of get a little bit older, you feel more okay saying simple things in a talk. You don't have to say the most complicated things. So I'm going to say a bunch of simple things. It's also the first talk of the term. So let's start really simply. So one question is, we could also define a kind of random variable. So let's say maybe we take some subset of Rn, maybe some Borel measurable set. Borel measurable set, maybe it's even some compact set if you like. And you could define the random variable, which is, how many, I take a random lattice, how many lattice points do I have in A, right? So how many lattice points or primitive lattice points in A, right? So this is a function on X, which I can think of as the following. It's actually, what am I actually really doing? So if I want to understand the number of lattice points A in GZN, let's say that, if I want to look at the total, a funny way of saying this is actually the integral, but a correct way of saying this is the integral of the indicator function of A, d sigma all of GZN over Rn. Right, so, and if I wanted to count the number of A intersect GZN prim, the number of primitive lattice points in A, this is the integral of chi A d sigma prim of GZN. Right, and so what am I really doing here? I'm defining the Zegal transform, right? So I'm saying, say, maybe let F be some bounded compactly supported function on Rn. I can define maybe f hat, I'll say f hat all of GZN to be the integral over Rn of f d sigma all of GZN and f hat prim of GZN to be the integral of Rn over f d sigma prim of GZN. Okay. So this is, again, just kind of abstract nonsense, but now we can ask, for instance, what's the expectation of this kind of random variable, right? And this is what, I don't think necessarily maybe Zegal would have thought of it in this way, but that's what Zegal was doing, or maybe even going back, this is probably, the history of this probably goes back to Minkowski or even Hlofka, maybe. And you can say, right, so classical result.
Sorry.
Yes.
Could you go back to the two slides before on the definition for the sigma all and sigma prim? Okay.
Yes.
Sigma all. Okay.
So sigma all is all non-zero vectors. Sigma prim is just the primitive vectors.
Yeah, thank you so much.
No worries. Yeah, of course, the issue with GoodNotes on like a chalkboard is you can't have the previous, or at least I haven't figured out a way to have the previous slides continue to show up, which is a little bit frustrating. If this was a real chalk talk, of course, this thing would still be on the board, and that would be nicer. So of course,
unless you erase it, and then it will.
Yeah, that's right. So of course, this classical result, which maybe it's Siegel, or I'll just put Zegal on it for right now, is that in this situation, if I integrate, let's say f hat all of GZN d mu of GZN over xn, this is equal to, so maybe I'll actually kind of just drop the arguments of the function, right? So I'll say if integrate f hat all d mu, there's this beautiful result that says this is equal to the integral of Rn of f d Lebesgue, right? And so what this is of course by definition integral over xn, integral over Rn here, f d sigma. So maybe now I do need to put the argument in here. Maybe I'll call it d sigma of x, and then we do d sigma. Let's see, f of x. Let's call it, notation. I should have done this before. F of v, d sigma of x of v, and then d mu of x, thinking of x as a point in xn now, right? So sigma of x is a measure on Rn, and this is, and you can actually get this formula. So this is you can get this by kind of unwrapping and rewrapping an integral. And of course, you have this other classical formula, which says that integral of xn over f hat prim d mu is 1 over zeta of n, integral of Rn f d Lebesgue. So this is a kind of a result about, if you want to say about expectation, right? It's an L1 result. And so a natural question then is, okay, so I have this point process. If I understand its expectation, if you're a probabilist, the next thing you want to do is to say, well, what can you say about its variance, right? And so this is something I learned about now, 15 years ago, that when I was working, in the course of working with Margulis, we learned about this beautiful formula of Rogers, which helped you understand the variance in this situation, right? So what do you mean when you say you want to understand the variance? It means you want to understand the L2 norm here, okay? And so maybe I'll just state this because this is not the theorem I really want to state. I want to just say that maybe just for n bigger than or equal to 3, you can do f hat squared, integral of f hat squared d mu over xn, and you can explicitly compute what this is equal to. This is equal to the integral of f, and so this is the theorem of Rogers here. Rogers, integral of f over Rn d Lebesgue, quantity squared, plus I'm not going to write this full term out, but you can kind of write it out nicely, lower order explicit term. In particular, f hat is in L2. So this is f hat, what I've written is for f hat all is in L2 of xn mu. This is again, importantly, for n bigger than or equal to 3. I'll make a remark here that for n equals 2, f hat all is not in L2. But f hat prim is actually not just in L2, it's actually in L infinity of x2 mu of x2, and it's in particular it's in it's in L2. So what I'm saying is that this is all sounding very fancy, but what this is simply if you have a 2-dimensional unimodular lattice, let's think about f being the indicator function of the ball of radius 1. You can have lots and lots and lots and lots of vectors which have length less than 1, but only one of them can be primitive, essentially. Maybe 2, right? Or 4 if you count the positives and the negatives. But a bounded number of them can be primitive, but however, an enormous number of them can be non-primitive, right? So for instance, if you have a lattice with a vector of length epsilon, then epsilon, 2 epsilon, 3 epsilon, all of those will be vectors. And the measure of the set of lattices that have this is epsilon squared, which tells you that f hat all is not in L2. Okay. But f hat prim is, and just to advertise some of the work of a former student of mine, Sam Fairchild kind of corrected a mistake in Rogers. Rogers claimed a formula for n equals 2, and for the integral of f hat prim squared d sigma over x2, sorry, d mu over x2, and has also done some very nice work on Hecke triangle and done further work on something on generalizing this to something to more general Hecke triangle groups. And there's also some hopefully upcoming work with Claire Bourine and Sam with some interesting results in this direction. So I just wanted to mention that as a little bit of advertisement. Okay, so this is situation 1. If we have some time, I'm going to come back to another collection of results in situation 1, if we have some time, that this is some old work of myself and Anish Ghosh, where we look, again, inspired by work of Jens, go back and look at some old problems of Keston and some old work of Erdős and Kotz and others, But I'll come back to this if we have some time, but because I want to tell a couple of other stories. Let me maybe make, before I go through this full story, let me say that both Zegal and Rogers have a common proof idea which is, you can do it a couple of ways. You can do it one way, you can say, and they're kind of morally in some sense similar, which is SLNR equivariance plus an analysis of orbits. You say that this integral, you think of integrating f hat or integrating f hat squared as defining a functional, and on Rn or on Rn cross Rn. And you say then what we're integrating against is an SLNR invariant measure, and then you try and understand what those measures are, and that boils down to understanding what SLNR orbits are on Rn or Rn cross Rn. And so there's a lot of really beautiful kind of just trying to understand what various invariants are, and this is what Sam had to do very carefully here. In n equals 2, it's kind of fun to try and think about, there's a natural invariant of pairs of vectors, which is the determinant. Now I realize I'm probably saying a lot of things that make sense to the experts, but not to people who haven't seen much of this before. So let me actually, before I get too deep into the details of lattices, describe another situation which this framework works, and tell you a little bit about some recent developments there. And again, this is now situation 2, which is going to be what are called translation surfaces. And I'm going to be working towards some joint work with Yitwa Chung and Howie Mazer, and then some joint work in progress with Sam Fairchild and Howie Mazer. And here again, maybe I'll just make a quick remark that to Dima's point, again, we're going to have some G equivariance here, which is actually going to be a big help for us. And this is also the situation which Veech kind of studied initially. And there's a little story, actually, in some sense, Veech was inspired by part 1 of this story, because he went to, many of you have heard me tell this story before, but he went to a talk by Margulis in Lumini about the Oppenheim conjecture, or not the conjecture anymore, but then it was the theorem. And hearing Margulis talk about the Zegal transform, he got inspired to define what we now call the Zegal-Veech transform, which I'm going to tell you about. But first, let me tell you what the space is. So again, I want to tell you what X is and what sigma is. Here, X is going to be a connected component of a stratum of what are called translation surfaces. And I'm going to tell you what all of these are, and I'm going to draw you some pictures in a minute. And the map sigma will be the following: sigma of a translation surface. Let's say I'll call it sigma of omega. I'm going to use omega to denote this. So omega will be some point at X. Sigma of omega will be the sum of delta measures at, I'll say Z, where Z is going to be in a set called lambda omega, where lambda omega is going to be the set of what are called holonomy vectors of saddle connections. So let me tell you what all of these things are. So if you haven't seen these, they may sound very fancy and intimidating, but all they are is they come from drawing pictures in the plane and playing Pac-Man on funny shapes. So what do I mean by this? So what's a translation surface? So what is a translation surface? And please tell me if I'm going too slow at any point, please tell me. I'm happy to go through some of this stuff quicker, but I feel like, again, it's the first talk of the term. Let's go a little bit slower rather than faster.
Excuse me?
Yes.
Could you go back to the previous slides?
Sure.
Connected components of a what? Of
a stratum of translation surfaces. Stratum. So I have to tell you what all of these words are.
Yeah.
So Yeah, so what is a translation surface? So first of all, translation surface, okay, so there's a Euclidean geometric definition. Euclidean geometry it's a polygon, Euclidean polygon, sort of sitting inside of C, or collection of polygons with parallel sides identified by translation. So maybe it's easiest to just see an example. So what a classical example is, of course, this is a common example, is just the torus. You take a square, you identify opposite sides, and you get this nice flat torus. Of course, this is what I drew in 3D is not flat, but it's you have a flat metric on it coming from these identifications. And this is, of course, you could have that guy. You could also maybe draw this one. This is another flat torus. You could draw kind of a long, thin one. This would give you some kind of longer, thinner flat torus. So you have a whole space of these, right? Something like that. But you could also take something like, let's say an L shape. I'm not insisting my polygons are convex, and you could identify opposite sides. So maybe this side is identified to this bit. Pink, I know, is probably not the best color on this chalkboard. Maybe yellow is a little bit better. This is yellow is glued to this yellow. This electric blue is glued to this electric blue, and this electric green is glued to this electric green. So what's going on there? What's going on here is this surface is now, well, let's make a little bit of a bad joke. Let's first complete the square. And let's identify the opposite sides of this. So maybe thinking of this as, so now what do we have? We have, if I were to do this, I would still get a torus, but now I'm going to get this little hole cut out of it. If I shade this hole in, I'll have this little hole cut out of it. And in the hole cut out of it, I'll have two parallel sides, which are, if you think about the identifying opposite sides of this, this would be kind of like a yellow, and this would be kind of a pink here. And so I'd have these two pink sides here and two yellow sides. And if I glue those together, I get a genus 2 surface, right? So I get another handle coming from this, except there's something funny happening at this point. Right? When you did this with the square, the four corners collapsed to one point, and you got, this corner got glued to this corner, got glued to this corner, glued to this corner, and that point had angle 2 pi, because all of these angles were pi over 2. And even here, right, the interior angles of your parallelogram, they will sum to 2 pi. But here, there's an issue. The issue is, of course, the corner where you have total angle. So let's see, let's try and keep track of the corner. So this is the left side of yellow, so it's here. It's the right side of green, so it's there. It's the top of pink, so it's there. It's the left of green, so it's down at the bottom. It's the bottom of blue, so it's the right of yellow. Oh, now it's the top of blue. And so, oh my gosh, all of these 8 corners collapse to 1 point, and the total angle is, if you do the calculation, it's actually 6 pi. So you have this particular point with excess total angle. You have a point with angle 6 pi only. And so we're going to keep track of those singular points. And we're actually going to think about this in a complex analytic framework in the following way. So in the complex analytic framework, complex analysis, which is kind of a nice way of summarizing all of this data, is taking a Euclidean polygon and identifying opposite sides by translation. Translations are certainly holomorphic. So I'm getting a Riemann surface structure, right? I have just a complex structure here, but I have more than that, right? Because I have dz, and let's do some basic calculus. D of z plus c is dz, right? Z plus a constant doesn't change the derivative. So what I'm actually getting is I get a pair, maybe I shouldn't call it X because X is something I'm using for my big space. I'll call it Y omega, where Y is a Riemann surface and omega is a holomorphic 1 form on Y. And for right now, there's a huge interesting literature on non-compact translation surfaces and so on, but let me think about Y as being compact for right now. And here's the point. The zeros of omega correspond to singular points for the flat metric in the previous picture. I don't want to go into an enormous amount of detail here, but there's actually a relationship between the angle. So for instance, if I look like sort of z squared bz, that's essentially up to a multiplicative constant, that's d of z cubed. And so that should correspond to, well, z goes to z cubed is kind of a triple, this is a z goes to z cubed is kind of a triple covering map, right? Over, it's branched at 0. And so you're going to get an angle of 2 pi gets turned into an angle of 6 pi. So total angle at the point is 6 pi. And now your favorite theorem on Riemann surfaces tells you the following. So the sum of the order of the zeros, which is also equal to the sum of excess angle divided by 2 pi. So the excess angle divided by 2 pi is the order of the zero, is equal to 2g minus 2, where g is the genus of y. So this is the classical, and we're really going to think about holomorphic one form. So again, if you don't like the language of one forms, just think about drawing graph paper on your Riemann surface. If you like the language of one forms, that's fine. It just means a one form is something you can integrate over a curve to give you a number, right? That's what you should think about it as. Okay, so what's a saddle connection now? So okay, what's a stratum? First of all, I should tell you what a stratum of translation surfaces is. So what I do is I fix the combinatorics. So I fix an integer partition of 2g minus 2. And I define, let's say alpha. So alpha is maybe alpha 1 through alpha k. Summation alpha I is 2g minus 2. And I define h of alpha to be the space of translation surfaces with this data. Surfaces with 0 pattern alpha. Okay, and I'm also just going to make a quick remark. We can define the area of a translation surface, y omega, to be I over 2 integral over y omega wedge omega bar. Now, I might be missing a minus sign. Dami, am I missing a minus sign? I think I'm okay. Up to a minus sign. I'll just put some absolute values on there. So the area of this is actually just the area of this as a polygon. And I'm going to really think about this space H1 of alpha to be the space of area 1 translation surfaces. And you might be saying, what's the equivalence relation? The equivalence relation is biholomorphism that takes one form to the other. Right, so that's the equivalence relation here. If you like to think about Euclidean geometry, that actually boils down to the same thing as cutting up the surface, re-gluing it, and kind of pasting it back together. So these are up to biholomorphism / cut and paste. So let me draw you an example of some things in H of. Let's draw some pictures of things in H of 2. So H of 2 means you have 1, 0 of order 2, you're a genus 2 surface. So I've already shown you this L is in there. Of course, I could have drawn some kind of much different shaped L. I could have drawn maybe some tilted looking L. So whatever font you like, you can draw your L in that font. I mean, not whatever font you like. I still want my lines to be straight. I could take a regular octagon and glue opposite sides. That's not terribly regular, but it's close enough. And these are all examples when you identify these opposite sides here of surfaces which have are genus 2 with one singular point. And so now, what are saddle connections? A saddle connection is simply, well, these points, these singular points are where I've smashed all the negative curvature on these surfaces, right? A higher genus surface has negative curvature, and I've flattened it out everywhere. So I have to smash the negative curvature into some collection of points. And so I've smashed the negative curvature into this finite collection of points. And now I think of those as saddle points. So a saddle connection is simply a point that connects saddles. So it's a geodesic in the flat metric. So gamma is a geodesic in the flat metric on y omega, connecting to not necessarily distinct zeros of omega with none in the interior. None in the interior. Okay. And so, for example, let me draw you some pictures of some interesting saddle connections. So for instance, if I take this L and the identifications are like what I've drawn before, you know, so here I'll draw some saddle connections in yellow. That's a saddle connection. So is that. That's also a saddle connection. So is that. These are all saddle connections. So are each of the sides. That's a saddle connection. That's a saddle connection, right? Each of these are all geodesics in the flat metric. All of these are saddle connections, but so are something more complicated, right? I could go halfway up here, come here, and this is now not, this is still in the interior, and go halfway across. That's another saddle connection. I could go a third of the way up here, come down 2/3, and then go up. That's another saddle connection. So I have this huge family of saddle connections. And associated to each saddle connection, I define z gamma to be the integral of omega over gamma. This is a complex number. This keeps track, let's say this was made up of 3 unit squares. So this is 1, 1, 1, 1, 1. I can tell you what the whole, maybe I'll do some of these in different colors. Maybe I'll make this guy, this guy pink. So this is going halfway up and all the way across. And I'll make this guy green, the one that goes a third of the way up. Third. And I'll tell you what the holonomy vectors of each of those are. So z of the green guy is equal to, well, I've gone up 3 times, and going up costs me 2. So, and I've gone across 1. So this would be 1 plus 6i. And the pink one, I've gone across twice, and I've only gone up once. So it's 4 plus I. And then, for instance, if I wanted to, maybe I'll make this guy electric blue. This electric blue one, it goes up 2 and across 1. So that would be 1 plus 2i. Right, so this just keeps track of how far you've gone horizontally and how far you've gone vertically. Does that make sense with what I'm defining as a holonomy vector? So now here is the beautiful punchline here, which is the set. I'll define lambda sub omega to be a set where gamma of z gamma. Gamma is a saddle connection on y omega. So now I'm going to define, I have this space H1 of alpha, then the map sigma is now to measures on R2, which I'm just going to say C is the following. Sigma of omega is summation delta measure at Z in this set of saddle connections. So first of all, why do people care about these things? Well, these are interesting geodesics with respect to a flat metric. These are a very special family of geodesics. 2, this comes up when you study billiards and polygons. These correspond to certain special trajectories for billiards and polygons. But many of you have seen this picture already and know it and like it. And how does it fit in? And this is this beautiful picture of Veech. So there's a natural probability measure, mu, H1 on H1 of alpha, which is SL2R invariant. There's an SL2R action on this simply by taking your polygon and transforming it linearly. And this is called maybe, it's the names are probably Mazur, Smiley, Veech, who, Mazur and Smiley and Veech independently kind of define this measure. And there's a probability measure on this, which is kind of like a Lebesgue measure on the space of surfaces. So imagine in this H of 2, you have all these different points, and what you really need to understand is you really need to understand these kind of 4 sides, right? You need to understand what this guy is, what this guy is, what this guy is, and what this one is. If you understand those four, you understand the rest because they're given to you. And so it's kind of a Lebesgue measure in this setting. I don't want to go into too much detail because I'm running short on time. But here's the point. You can define, Veech defined the following. He said f hat of omega. So if you start with a function which is bounded and compactly supported on C, you define f hat omega to be the integral over C of f d sigma of omega. In other words, it's summation over all saddle connections of f of z. Veech proved the following beautiful, beautiful formula. Veech showed that the integral of f hat d mu over your stratum, that there was a constant c h1, so that this is the integral f d Lebesgue over on C. And this is called the Zegal-Veech formula for kind of obvious reasons. It's an analog of Zegel's formula. And again, as Dima points out, the key point here is there's an equivariance. Equivariance under SL2R. So the, in other words, sigma of G omega is G sigma of omega, or G star sigma of omega. And that's the crucial relationship here, plus proving, so once you prove this, which is essentially follows from the definition, the hard part is proving that f hat is actually in L1 of mu. Once you do that, you're kind of in business, because then you know that integral of f hat has to be integrating f against some SL2 invariant measure on R2, and then that's just Lebesgue. So again, it comes from classification of orbits. Let me mention now, so this is the question of, this is again the kind of expectation. It says if you take a random translation surface, the number of saddle connections in a ball or in your favorite set is proportional to the volume of the set, right? That's what this result says with the proportionality constant. These numbers, by the way, are very interesting. These are called Zegal-Veech constants. But so a question you could ask is, well, what about variance? So I should, oh, my screen disappeared. There we go. What about variance? I should mention that initially there was a paper where John Chaika and I were studying, it very much inspired by work of Jens and Andreas, the distribution of directions of saddle connections. And you should also see some, just to advertise, some recent work of my student Anthony Sanchez, and some previous work of a previous student of mine, Dia Taha, who studied some properties of these distributions as well in particular cases. So both of these are worth looking at. But John and I were studying the distribution of directions of saddle connections. And in our paper, in a little side note, we made the claim that f hat was not if in L2 of the strata. And now let me emphasize that this is actually wrong. What we had actually proved was that f hat was not in L3. And this was pointed out to us by Howie Mazur. Howie Mazur pointed out that our argument didn't show that this thing didn't have finite variance, it just showed it didn't have finite third moment. But so then working together with Yitwa Chung and Howie Mazur, it left open the question, does this thing have finite variance? And so we showed that in fact, f hat is in L2. So for f, which is bounded and compactly supported on R2, f hat is in L2 of H1 mu. And the key point here is you need to understand surfaces with lots of short saddle connections, right? You need to understand what does it mean to have lots and lots of short saddle connections, and you need to bound the measure of that collection of surfaces. And how do you do that? Well, you say that we basically built a bunch of models. We said, hey, here are the surfaces that can have lots and lots of short saddle connections. There's only a few mechanisms to get this. And then we bounded the measure of all of these different possible mechanisms. Now, again, why would you maybe care about this? Well, this I'll mention that it'll, in an appendix to the paper, myself and Rene Rohr recovered along a subsequence at least error terms for counting saddle connections. And I should mention here that there's the best possible results that I know of so far in this direction are by, not by myself, why do I keep saying that? It's by Amos Niveau, Rene Rohr, and Barak Weiss have some really beautiful results about counting. But again, the point is once you understand something about the variance, you understand something about counting at least almost everywhere. And this is a philosophy that's been used in a lot of different settings. In particular, you can ask I think Dubey's here. Dubey has a lot of expertise in using variance to get really nice counting results among other people here. Sorry if I'm not mentioning someone else who's here who's using this. And Dima and Michel Skendery have used this in the lattice setting to get lots of interesting and beautiful results. Okay, so I'm not giving many proofs. I'm trying to give you a big picture thing, but I do want to spend about 10 minutes going through the example 3. And here's the warning. There's no G equivariance here in this last example. And this last example may be kind of, well, I think it'll be familiar to many people in this audience, but maybe not as familiar. So let me spend a little bit of time on it. And this is, now my space X is going to be this moduli space of hyperbolic genus G Riemann surfaces. Space of genus G Riemann surfaces. And now I'm going to take a Y. If I take a Y in MG, I'm going to think about associating to it the following measure, sigma of Y is going to be a measure. Sorry, let me write this down a little bit more carefully in my notation. Sigma is going to go from X to the set of atomic measures on the positive real numbers. So it's not going to be higher dimensional anymore. It's going to be positive. It's going to just be the R1. And sigma of a Riemann surface or a hyperbolic surface Y, so Y is a point in X now, right, is going to be the summation over all gamma is a simple closed curve. And it's going to be the length of that curve. Sorry, I don't know why I put that down there. It's going to be the delta measure on the length of that curve on the surface Y. So Ly of gamma is the hyperbolic length of the geodesic representative of gamma. So this is, I'm thinking of gamma as a homotopy class of simple closed curves, and the length is the length of the geodesic representative. And now there is a question, which is, well, for instance, you can ask, and this is famously asked by Mirzakhani, you could ask, what is sigma of Y of the interval 0L is the counting for number of simple closed curves of length less than or equal to L on the surface. And what Mirzakhani showed is the following, right? She not only showed, she showed a pointwise result, which she said that sigma of Y of 0L, there's this constant out front, we'll call it B of Y, and then this grows like L to the 6G minus 6. But she was also able to say, if we integrate B of Y over the space X, D, now what's the X is mg, so let me just write mg down here. D mu V Peterson of mg, of Y, where mu WP is the V Peterson volume on the moduli space of hyperbolic Riemann surfaces. She was able to compute this explicitly and get an actual number out of this, an actual number. Okay. And in particular, what this showed, she essentially what she showed is that suppose you define, right? You start with F, which is bounded and compactly supported on R plus. You define F hat of Y to be the integral of F d sigma over R plus d sigma of Y, right? And then that's sigma of Y that's the actual measure. Then she was able to actually tell you what F hat of Y d mu WP of Y is. It's in the integral of F with respect to an appropriate density here. So all of what I'm describing here is part of Mirzakhani's PhD thesis. So I don't think she called it this, but I am trying to get this to be called the Mirzakhani transform. So I want this to be, I would like us to try and call this the Mirzakhani transform. Sorry. So start with F and define F hat. And she was able to give you this beautiful integration formula. So one of the reasons why this is extremely difficult in this setting is exactly because there is no G equivariance around. What's also cool, and this is, maybe I'll just mention this, is that just like Zegal used integration formula to compute the volume of Xn, so the volume of Xn is zeta of n down to zeta of 2, Mirzakhani used her integration formula to compute the Veech-Peterson volume of the moduli space MG. And this is, I think, a really remarkable set of results. But let me now just mention that this now leaves open the question of what about variance in this setting? And I'll just mention, and I won't go into great detail here, is that recently with Francisco Arana-Herrera, so Arana-Herrera is one name. He's now a postdoc at the Institute. We showed that this function B of Y, which we call the Mirzakhani function, we show that integral of B of Y squared d mu Y is finite. However, B is not in L2 plus epsilon. That's Mirzakhani had already shown that. Mirzakhani showed that it was not in L2 plus epsilon and that it was in L2 minus epsilon, but it had left the kind of question of whether it was actually in L2 open, and we resolved that. And again, what's the point? Why do we care about this? From this, we get results on counting pairs of curves and various configuration of curves, which is kind of cool. So you can say, I want to understand some families of pairs of curves. And then maybe just the last thing I'll say is going back to example 2, back to the translation surface setting, there's work in progress with myself, Sam Fairchild, and Howie Mazer to count pairs of saddle connections satisfying certain length and area restrictions using this kind of L2 formulation. So this might be a good place for me to stop. I realize that I've gone through kind of a lot of material, but what's the point here? The point is this perspective, thinking about you have a moduli space of geometric structures, and associated with each geometric structure, you have some points, some collection of points or a measure on a Euclidean space that allows you to think about a measure on your space of geometric structures that's giving you a point process on a Euclidean space. And then thinking about things in terms of expectation and variance allow you to get interesting results back about the geometric structures. There's actually many, many more statistical questions you can ask. You can ask about the distribution of things like directions. You can ask about finer scale distribution questions. And then this leads you into, for instance, Jens's work among other people, and then further kind of number theoretic and Diophantine things, which I didn't end up getting to today. But hopefully the point was that all of these things kind of have a very big spiritual similarity. Whether that helps you prove things is a different question, but I think it helps you formulate questions. Certainly it's helped me formulate questions and then figure out maybe I have to use different ideas to prove things. In the end, even the proofs are often spiritually similar in that you're trying to understand what the non-compact part in all of these things. The key point is understanding the non-compact part of the moduli space, trying to say what happens as you go to kind of infinity in the moduli space. That's what's kind of controlling everything, and understanding that is the key issue. So thank you for paying attention, and I think I will stop here.
Okay, well, let's try to give a nice live round of applause by unmuting ourselves. Let's have some sounds like this, or maybe some reactions with those clapping hands. So any questions? We still have time for questions. So can you elaborate on this non-invariance of part 3? So you have, I mean, SL2 acts anyway, right?
In part 3, SL2 doesn't act, right? Because we are acting on, it's MG. Oh, so my screen has gone white. Why? Okay, maybe I stopped sharing because I just.
Yeah. I see. You have MG, right?
Yeah, so it's MG. It's not the moduli space of quadratic differentials. It's actually the moduli space of hyperbolic surfaces. Mm-hmm. So I'm not sure what the right way to think. There's no group, no Lie group certainly acting on this thing in a way that I can understand at least. Maybe there is some. Maybe this is some shadow. Maybe this thing is some shadow, some invariance. But I don't know how one would even speculate about that. So there's no equivariance here, and this is what makes it hard, right? Because what Mirzakhani wants to do is she wants to compute volumes by saying, oh, I'm going to cut along this curve and I'm going to break it up into smaller pieces. And then I need to understand the volume of the things with this fixed curve. And this is what, this is how Zegal gets induction for his volumes of the space of lattices. But there you have this invariance to give you this integration formula. Here you need hyperbolic geometry. This is kind of, there's McShane type formulas or what's hiding behind this integration formula.
Other questions?
Can I ask, thanks for the great talk, Jayadev. How about higher moments in this setting? Does one know if they will be finite or will they diverge?
In the hyperbolic curve setting?
Yeah.
So at least this function B is not in it's not in L2 plus epsilon. So L2 variance is the best you can hope for. I hopefully in a little bit actually, hopefully this we'll actually be able to share some of this stuff soon. So Mark Bell, Francisco, and I are working on some numerical experiments to try and understand the following question, which is not exactly this, but it's related, is take a pair of curves and simple closed curves, look at the intersection number. That should be related to the product of the lengths, right? Like a heuristic, the first guess for an intersection number might be the intersection number is just the product of the lengths, right? You cut the surface up into little squares. And so we actually have some really nice numerical plots of the distribution of intersection number versus product of the lengths. Why am I mentioning this in your question about moments is because this is in some sense giving you at least a statistic of the Thurston measure that's actually showing up here. So it's telling you something about tails. I'm not sure exactly what it's telling you, but it's telling you something about these tails. But this function B, this Mirzakhani function, is not in L2 plus epsilon. It's just in L2.
Thanks.
Other questions? Okay, well, I think this was a good start.
So maybe I'll mention just one question related to what Jens said.
Ask yourself a question and answer.
Yeah, this is a question for the audience, which is, okay, so I know some of you in this crowd like, we all like higher rank Lie groups. And so MG is, of course, you can think of as the space of representations, discrete faithful representations of the fundamental group of the surface into SL2. Because you're thinking about your surface as H2 mod the, hyperbolic structure is thinking of your surface as H2 mod the fundamental group, where the fundamental group sits inside of the isometry group. You can also look at moduli spaces of representations of your fundamental group into higher rank Lie groups, SL and R. The I prefer not to call it higher Teichmuller theory, but that's what some people call it. We could call it, say, Goldman-Hitchin theory or something like this. And there you can also define, you can ask, hey, I want to count elements in my fundamental group where the largest eigenvalue of what I'm mapping to is smaller than something, and you can try and do this counting. And then you could ask similar questions there about, counting and L2 questions. So this is something I think would be extremely interesting, and I want to just suggest it to this crowd because I think this crowd may have the expertise to think about this problem.
Okay. Any comments from the crowd?
Jayadev, I have a different question and unrelated to this.
Okay.
You mentioned that it's in the context of translation surfaces that this function is in L2 but not in L3.
Yeah.
And so somewhere in between, basically, it's going to be, your argument gives just L2, or is it?
No, our argument gives you a little bit more. It gives you, if you look in the paper with Howie, well, I think the proof gives you L2 plus a little bit depending on the stratum. We make no claims that this is optimal. So there is some lower bound on what LP it's in, and there's the upper bound, which is 3. I don't know what the actual answer is, and I think that's actually an interesting question, just in and of itself. Yeah.
And would it be? Do you think would be the same for every F, or would it depend on for every, let's say, compactly supported F, or would it be?
The statement I would like to say is that if you have the statement I would want is to say a bounded compactly supported function guarantees you're in. Whatever. So I don't know if it's going to be the same for, I think I would expect yes, but yeah.
Okay. So anyway, thanks again to Jayadev. It was a great beginning of the semester. So let me stop the recording now and wish everybody a great week and a great weekend, and see you guys around next time.